if and hopefully there is no conflict. If you have conflict, I can overstay. So hopefully there won't be any conflict with MMC. It's 20 questions and it's multiple choice. And already told you you can skip kinematics 1D, kinematics 2D, so you can skip projectile motion and start from test number 2 and test number 3. Okay. However, you do have rotational kinematics. So that was this unit here. Okay, so a few questions from this unit there. And then from dynamic rotational kinematics, remember moment of inertia, so laziness when it comes to rotation. Remember that a solid sphere has the lowest moment of inertia. And between the ring here, the cylinder, and the solid sphere, this one has the lowest moment of inertia. You can see that with the coefficient here. And this one has the largest moment of inertia. So when it comes to rotation about an axis of rotation, rotation about an axis. Okay, so about rotational kinematics, so that will be unit 8.1. Okay, so that's what we did last week. And just to, it works like kinematics 1D. So for example, like you need to know that the acceleration, so the angular acceleration or the rotational acceleration is how fast you are spinning faster, right? So the unit is rad per second, and the definition is the final speed, but this is rotational speed minus the initial rotational speed over the time elapsed. Okay, so the unit again is rad per second. Okay, so it's going to be very simple. This part, some students have an issue with understanding that one revolution, it's the same thing as 2 pi rad. Okay, so it's like units, right? The same way you say 1 kilometer is 1,000 meters, for example. So one revolution is 2 pi rad. So you can use proportion. And 2 pi rad, of course, is the same thing as 360 degrees. So you go around a circle once. So it's the same thing as 2 pi r. Okay? So for example, if you have 33 RPM, so that's omega. So how fast it's spinning, but the unit is revolution per minute. So if you need to convert that to rad per second, you're going to say one revolution is 2 pi. So you're going to do 33 times 2 pi per minute. So 1 minute is 60 seconds. So you're going to divide by 60. Okay, so that's how you can convert. Okay, we talk about the linear speed versus the angular speed. So let's try to make a nice circle. It's a nice circle, but I cannot move it. Okay, it's right here. Okay. So that's the radius R. So what we call the tangential or linear speed, you see, this is the linear velocity V. Okay, and let's say you have a mass here spinning, omega, or maybe it's like a disk, right? It's a vinyl disk, right? So it's spinning, and the rate is omega. So it could be, for example, 33 REM. The relationship between the linear velocity and the angular velocity, we already talked about that. It's going to be V equals the radius times omega. So this is called the tangential velocity or the linear velocity. The unit is meter per second. R is in meter and omega is in rad per second. So it's consistent because rad does not count. Radians does not count, right? So here you have meter per second. So here you have meter per second as well. So remember, we already talked about that. I show you like small animation. So this is the velocity here. If you go half the radius, it's going to be the same rate of spin, but the velocity will be divided by 2. And if you have a point here, the rotation is the same, the spin rate is the same, but the velocity equals to 0. Okay, for some reason, sometimes it doesn't go well. So hopefully now it's clear. So a few questions about rotational kinematics is the same equation that you use for linear kinematics, except you replace acceleration is replaced by alpha, and then the velocity is replaced by omega, and the distance here is replaced by the angular displacement.
So half the radius you would have half the velocity, but you said what would be constant?
The spin,
Oh,
the spin rate, right? So this guy at the center, he is spinning about its axis, right? So he has the same rate of spin that everyone else. So he has the same number of revolution per minute. However, he's not going anywhere. So the distance is 0. So the velocity, the tangential velocity is 0, but omega is not 0. So all of them, they have the same number of revolution per minute. However, the linear distance is not the same. The one at the edge is covering more distance for the same amount of time, so the velocity will be the largest, right? So V is proportional to the radius for the same omega, okay? Okay, what else do you need to know? So that will be for rotational kinematics. What else? Um, and then you have what it's called the work energy theorem. And that says that the net work done on a system equals the change in kinetic energy. It's a different way to express the conservation of energy. So if there is energy transfer to a system, that energy will go to the energy of motion. So what's the change in kinetic energy? That will be 0.5 times the mass times the final speed minus the initial speed. So what's the definition of work? Here you have to be careful. If it's work done by friction, the work will be negative because friction is trying to slow down the system. If it is work done by applied force, then the work will be positive. Okay, so that means you are putting energy into the system. So for example, if you have a mass here, m, and it's moving over displacement delta x, and to keep that simple, you are pushing. We are pushing on, you are applying a force here, F, push, it's a push, but you also have kinetic friction here. So the network done on the system will be the work done. Okay, so I'm moving in this direction. So the work done by the applied force, so it's just the force times the displacement, because P is parallel to the displacement, minus the work done by kinetic friction. That will be equals to the change in kinetic energy. Now, if the forces are the same, if they balance out, so that means there is no change in kinetic energy because there is no acceleration. So that means the net force is zero and there is no acceleration. Okay? But the work done by friction on the system is always negative because it's removing energy from the system. Okay? Now remember that kinetic friction is the coefficient times the normal force. And that will be in magnitude. Okay, there, forget about the minus. When you are using this equation, there is no minus. So the normal force, it depends if you are pushing on the ground or not. If you are not pushing on the ground, or you're not pulling on a string, then up equals down. So you see the weight here, and you have up the normal force here. You push on the ground. The ground is like little springs. It's like a bathroom scale. Okay, little spring, the old bathroom scale. My time bathroom scale. So you push, and it's gonna push back. So in that case, you just have the normal equals the weight. It doesn't have to be this way, right? If you apply a force, for example, if you apply a force this way, okay, so now if you apply a force this way, you see that vector has a tail and a head. It has a x component and it has a y component. So in this case, you are pushing down more. So in that case, the normal force, okay, will be equals the weight plus that y component of the push, right? Because you are pushing harder. The spring here, those molecules, part of the ground, are more squeezed, so they're going to fight back. Okay? If you are finding the work done by P on the system, okay, and if it's not parallel, you have to use this component here because this component is not helping the system going faster. It's just pushing it down. So when you are finding the work done by the applied force, you only use this component here, which is the x component times delta x. Okay, so then you will have to change that equation here because here you're going to have a cosine somewhere. Here I just multiply. This is in magnitude. Okay? Question? So if the speed is changing, then there is a net work. If the speed is not changing, that means acceleration is zero. That means the net force is zero. That means the forces balance out. And at the end, the system does not increase its level of energy. Okay? And what else? Yes. Okay, question. So this is called the work energy theorem, and it's like very much the conservation of energy, right? You can do it a different way. You can say energy before equals energy after. So you can say, okay, energy before, that will be kinetic energy before plus energy that you transfer because you apply a force on the system minus that work done by friction, the work done by friction will be kinetic energy after, the same thing. Okay, so work is energy in transfer. Imagine a system is like a reservoir and you are adding energy to the reservoir. So when you are burning fat or glucose, you are making ATP. So you increase the energy, the reservoir, right, of the system. Or you can remove energy if friction is involved. Is that clear? If we are talking about static friction, then nothing moves. If nothing moves, no work is done. Okay, and then do
Sorry, but what situation are you using the Y component of the push?
no, the Y component of the push is not for the work, right? If it's this is the X component, this is the Y component. You are using the Y component if you need to find the normal force, because this is mg and now the normal force is there. So the normal force has to balance out not only this Y component plus mg. So in that case, when you are pushing at an angle, the normal force will be equals to the Y component of the push plus mg. If you are lifting, it's going to be the opposite. The normal force won't be as strong because imagine the ground is made of those little molecules that are squeezed, get upset, and squeeze back. So if you are pushing into the ground, you are increasing the normal force. Okay, so you use the Y component when you say up equals down. Okay, so Newton's law. So you have inertia. A body that is at rest wants to stay at rest. A body that is moving wants to stay moving at the same speed in the same direction unless acted upon by a force. And Newton's third law, which is non-intuitive, for every action you have an equal and opposite reaction. So you cannot push harder that you are being pushed, and you cannot be pushed harder than you are pushing. So the force is always the same, impulse is always the same. What is not the same is the consequence because it depends on inertia, but the force is always the same. So Newton's second law says that the acceleration of a system, okay, of a mass, equals to the net force. Okay, so the net force. So if you are along the x-axis, it will be right minus left or up minus down over the mass. So for the same force, acceleration that means inversely. So the acceleration is inversely proportional to inertia. So for a linear motion, inertia is just the mass. So for the same force, if you multiply the mass by 2, acceleration will be divided by 2. So acceleration is proportional to the net force. Okay? Now, Newton didn't write his second law this way. He didn't write it this way. He wrote it a different way. He said if you apply a force during a time t, the velocity will change, but how much of it will change depends on the mass. So he wrote it this way. The same thing. Okay? So if you apply a force during a time t, the momentum will change. So this is called the change in momentum, and this is called the impulse. Newton second. This is kilogram meter per second, but it's the same units, right? If you work out the Newton, you're gonna get the same unit on both sides. If there is a change in momentum, then there is an impulse. Impulse is like a kick, right? So momentum is mass times velocity. Okay? So Newton's three laws of motion. And then what else? Okay, and then you have something called a torque equilibrium. So the way I do it, we don't have to do it this way, is the sum of the clockwise torque equals the sum of the counterclockwise torques. If you do it this way, forget about the negative sign. Okay, because I'm just considering the magnitude. Otherwise, if you want to do it like your textbook is doing, then you will have to say the sum of the torque equals 0. And then you have to say if it's clockwise, it's a negative torque. If it's counterclockwise, it's a positive torque. But if you do it this way, do not worry about negative. There is no negative if you are doing this way. So this is called torque equilibrium. So typical example is like you have a seesaw here and you have a big mass, for example, M3, and you have two small mass here, M1 and M2, and this is called the fulcrum. Okay, and then what that will be the distance d1. So it's always the distance between the force, so that will be the weight. There is weight, and the axis of rotation, that will be here d2, and that could be d3. Now, if you are doing this, don't worry about the unit. So you can have kilogram on one side as long as you have kilogram on the other side, because it's an equilibrium. So an equilibrium, it's like you have a scale, right? So if you go from kilogram to Newton, you're going to multiply by 10, but if you multiply by 10 here, you're going to multiply by 10 there. So it doesn't matter if it's an equilibrium. If you are asked to find a torque like force times the distance between where the force is applied and the fulcrum, so then yes, you want Newton and you want meters. But if you are doing torque equilibrium, you don't have to convert to Newton. You can keep kilograms if it's kilograms. You can keep grams if it's grams. You can keep centimeters if it's centimeters on both sides, because it's an equilibrium. So this is like an equal sign. Okay, so in that case, this one wants to make a, what is it? Clockwise? Is it clockwise? And this one wants to do counterclockwise, and this one wants to do counterclockwise. So the sum of the counterclockwise equals to the sum of the clockwise. So of course it's going to be the weight. The force is the weight here. Okay, you have weight number 1 and weight number 2, and here you have big weight number 3. But I don't care about Newton. Okay, I can keep kilograms if I am given kilograms. So I will say M1D1 plus M2D2 in magnitude equals M3D3. If you insist to use Newton, you can do that. You can say weight 1 D1 plus weight 2 D2, weight 3 D3, because to go from here to there, you multiply by 10, but multiply by 10 on both sides is okay. right? If this is equals to that, and you multiply by 10, it's going to be the same. Okay, so this is called the torque equilibrium. We agree? I'm glad we do. Okay.
Okay, yes, now stay.
And then you have force equilibrium. Okay, this we already work a lot about that. It's when you have sum of the left equals sum of right, in magnitude, and sum of up equals sum of down. And torque equilibrium, which you have seen. So it's the sum of clockwise equals the sum of counterclockwise. And once you have what is called a static equilibrium, that means both conditions are met. Those two or three equations if you are in 2D. So this is very big if you go to physical therapy, for example. Now they have doctorate, you can go to graduate school. And I think it's a great field because with all those people working on computers and being on their cell phone all day long, you're going to have a lot of clients. So anyway, this is big in biomechanics. Okay. And then that was, I think, for test number 3, you have conservation of momentum. So the only tricky thing here is that you have to remember that momentum is a vector. So each time you see a problem with conservation of momentum, you have to do this. Left is minus, right is plus. That's the only thing that could be tricky. So if something is moving to the left, that means the momentum is negative. Okay, so momentum is a vector, but because it's in 1D, we focus on 1D. You could do it in 2D, it's just more math, but it's the same, and vector analysis. But in 1D, we forget about the arrow, but we remember that it can move to the left, so it could be negative. Okay, so conservation of momentum means that conservation of momentum, you use it when, I don't know, they collide. Okay, you can have M2, M1, and maybe they're going to collide with each other, and they could be bouncing off, which is elastic collision, or they can stick to each other. So when they stick to each other, some energy, kinetic energy, is lost. If they bounce off, totally bouncing off, that means kinetic energy is conserved. If they stick to each other, some of the energy goes to noise and damage done. So anyway, you have to be careful that the momentum before here is negative. And then they can stick to each other, so that will be before. And which one has the largest momentum is going to win. So this way, we don't know. You have to multiply the velocity by the mass to see which one will win. But one of them will win if it's hit and stick, right? So if they hit and they stick, let's say this is the winner, maybe they're going to move this way. Okay, so you have to be very careful with the sign. So anyway, conservation of momentum for collision means that m1 v1 plus m2 v2 equals, this is just v2, m1 v1 prime plus m2 v2 prime. If they stick, then that means v1 prime equals v2 prime equals v prime. So it's of course they simply stick to each other. They're gonna have the same velocity after. Yes, but you have to be careful that in that case, this term here will be negative. And if they have the same velocity after, then you have to factor out, right? So if you have 30 potatoes plus 20 potatoes, that will be 50 potatoes. It's called combining like terms, right? Okay? Okay. Mm-hmm.
There does it say a stop?
They stick to each other. They stick to each other. Okay, they stick to each other. In that case, hit and stick. So they have the same final velocity, but be careful, the final velocity will be negative. So if you have a multiple choice, with one is positive, one is negative, you want to make sure you go not too fast and the answer will be negative. Okay? And then if we have a recoil situation, like two ice skater, we already did those multiple time. So before the momentum equals 0 because nothing is moving. So that's before. And they push. So after. So the one with the more mass will go slow. And the one with less mass, tiny one, will go faster. So it's going to be m1 v1 prime plus m2 v2 prime. And a recoil situation, you have m1 over m2 equals minus v2 prime over v1 prime. So that's a recoil situation. You did have that for test number 3. Okay, so the total momentum is 0 before and after because the momentum is conserved. If we neglect the external forces, right?
Can I ask, in the before, what's going on? Are they like colliding?
No, they push. They are like ice skaters, like pushing each other.
Oh, okay.
Or a rifle, right? Or a gun. It's a gun with a bullet inside. Nothing is moving. And after you shooting range, this one is moving this way and this one is moving that way. But before, there's no momentum to begin with. I don't know if I know how to draw a gun. That will be my gun. I didn't evolve since kindergarten, so that's a gun. When it comes to drawing, I didn't improve much. Okay, and then energy and power. Right? So by definition, the average power, it's gonna be the net work done, or the work done by a force. It should be by a force, right? So it will be the work done by a net force on a system over time. So that means power is how fast energy is consumed, how fast energy is produced. So it's a rate. So it's the energy transfer per unit second. Okay, so it's also equals to the force times the average velocity. So that will be another definition. So the unit for power is in watts. So this is also the change in energy over the energy transfer per unit second. So energy is in joules, time is in seconds, and power is in watts. So I can say also the energy, okay, or the change in energy in joules, it's the power in watts times the time in seconds. But joules is a small unit. So if you want to pay your bill, electric bill, and if they use joules, you're going to end up with 10 to the 6, 10 to the 8, and people don't know how to use scientific notation, and they're going to go on panic mode, and they're going to call the electric company. I don't understand. What is that? A 10 with a 6, a little 6 above. I don't get it. So they use a different unit of energy, right? They're going to use kilowatt hour. It's still energy because here you have power and here hour is time. So that in that case, power will be in kilowatt and time will be in hour. Okay, so in that case, 1 kilowatt is 1,000 watt. Okay, and then I will tell you in New York City, for example, the price for a kilowatt is about 25 cents, which is a lot, much more expensive than here. So if you are, I don't know, if you are using right now they are using heat, right? Because it's super cold in New York City. So 10,000 watt heater, I'm just making things up. That will be 10 kilowatt. And if you are using for 24 hours, okay, you will have your energy spent will be 10,000 times 24 kilowatt hour, and then you multiply by 25 cents to have the amount of dollars. So if you have a question about that, it will be an open question. You need to put the answer. And every semester, not every semester, every year, I got people who do not understand what a 1 cent is. 1 cent, right? So just in case you are among those people, $1 is 100 cents. Hopefully you know. Every year they don't know what a cent is. A penny. Right, so $1 is 100 cents. So you have to convert cents to dollars. Okay. Any question? We good? Yes. One. This one. Okay. What else? Um, the work done by gravity. You see gravity. The work done by gravity on the mass, right? It's just the force times the displacement, so it will be the weight times delta H, right? So if you have a mass here, you start from point A, you go boom, 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 boom. I change my mind all the time. I don't know where to go. Okay, I'm gonna go here. Looks good here. Okay, so the work done by gravity only depends on the height. So the work done by gravity on the mass is just the mass times, so the weight times delta H. Okay? So the work done by gravity can be negative or positive. So in that case, it's going to be negative, right? Because it's if you are moving it up, it's trying to slow you down. But anyway, that's mg delta h. That will be also equals to the change in potential energy. Okay, so potential energy or the change in potential energy only depends on the difference in height. So if you go from point A and you go boom, 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 go to the library, go to Starbucks, blah, 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 go back to here, the change in potential energy equals 0 because you came back to the same height relative to the ground. Okay, so potential energy only depends on the height above the ground. Okay? Now, open your listening ears. Pay attention to what I'm going to tell you now. Let's say I'm looking above, right? So I'm using a drone. I'm looking at someone pushing a box. So this is someone here pushing the box, and I'm looking from above. And he's pushing the box for exercising. It's in the gym. You know, you have those sled that you can push. So just pushing and come back to here to put the sled back where it was. So he's pushing, but he's going to have friction, right? He's going to have kinetic friction. That's the idea. You want to have friction to have a good workout. Now, the work done by friction on the sled, I think it's called a sled, will be equals to negative. So it's a negative because the work done is negative because it's taking away kinetic energy. The kinetic friction times the distance. So what is the distance? The distance will be all this, right? It means you are taking a measuring tape, like a string, and you are measuring that distance. So friction is not a conservative force like gravity. It does matter the path that you take. For gravity, it does not matter. Okay, the work done by gravity, all matters is the initial position, the final position. That works for all conservative force that involves potential energy. Here, there's no potential energy. You are not storing anything. So the work done by friction will be the frictional force times the all distance here that you can measure with a tape. The work done by you, if you are pushing here by your push, it's the same thing, okay? The work done by the push on the sled, it's going to be push times D. Okay, so if you balance out, if the push equals to the friction, so the net work equals 0 because there is no acceleration, because there is no net force. Of course, if you are pushing harder, if you overcome the kinetic friction, so yes, you do have an acceleration. So yes, there is a network. So yes, there is a change in kinetic energy. Now, if I ask you some problem, one problem, if I ask you what's the distance, so I'm always surprised that people don't know theirs. It's not your fault, it's the teacher fault, I don't know, math teacher, or maybe it's your fault. But the distance around is 2 pi r. Okay, it's called the circumference. And some students say pi r square. No, because this is distance times distance, which is an area. This is one distance. So the area is pi r square. 2 pi r is the distance around a circle. Okay? Next. Should I upload the lecture or not? I should. So conservation of energy. No, it's just to piss off those who didn't come. That's why I was thinking. But you'll I'm gonna postpone till tomorrow before posting it. Okay, conservation of energy means energy before equals energy after. So for example, kinetic energy before plus potential energy before. If there is no friction involved or no air resistance involved, okay, so energy is not lost. It's an isolated system, so no exchange of energy with the outside. So then I can say total amount of kinetic energy before plus total amount of potential energy before equals total amount of kinetic energy before after plus potential energy after. So that will be 0.5 the mass V1 square plus mgh1 0.5 mv2 square plus mgh2. The most simple case when there is no friction and no work done on the system. So it's like a reservoir here. Okay, you start from some kinetic energy and then potential, and you keep the same amount of energy because there is no friction or air resistance or nothing that you add to the system. So maybe you're going to have more kinetic and less potential, but the total amounts here stay the same. Okay? So typical question is when you throw something in the air, right? It's going to go up, go chi 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 chi, and you have some height. So you start with kinetic energy and then goes to potential energy, right? So that will be 0.5 mv squared equals mgh, boom, boom, and you have final speed equals 2gh. Okay, we did some problem like this, super easy. You can get the same thing using kinematic equation when I ask you to find the maximum height. You can do that with kinematics as well. Okay, copy me. You good? Okay, equilibrium, static equilibrium again. Let's say push-ups. Push-ups are very hard. I cannot do push-up on the ground. If you can do push-up, good for you. So this is me in the future when I will be able to do push-up. So this. No, I don't look good, right? I'm gonna try again. Okay, doing push-up. Okay, I can't. No, if you can, it's good for you. Okay, free body diagram. So okay, so what will be the forces acting on this person? It's not me, it's another person. So you're gonna have normal force here, right? So you have a normal force each time there is a contact with the ground. You push on the ground is gonna push back on you. So that will be a normal force. And then you have a normal force also because your feet are touching the ground, right? So you're going to have another force here, maybe not as much, N1. So you push on the ground is going to push back on you. And then you have your center of mass somewhere there. And here you have the weight, mg. Okay, not bad. So it's a static equilibrium. So if you are using torque, for example, And now you have to decide where to put your fulcrum. You can place the fulcrum wherever it's good, right? Wherever it's useful for the computation that you want to do. So let's say I'm going to put the fulcrum here at the feet. So in that case, the torque applied by N1 about the axis of rotation is going to be 0 here. There is no torque because it doesn't help with any rotation. It doesn't make it rotate. So the torque applied by N sub 1 is 0. This one wants to do a clockwise, and this one wants to do a counterclockwise. Agree? And then you have that will be a distance g1, for example, from the fulcrum. The distance is always from the fulcrum, and that will be d2, for example. Are you with me? So the sum of the clockwise torque, okay, clockwise torque will be equals to the sum of the counterclockwise torque, right? Right? So it's counterclockwise, so it's going to be N2 times D2 equals mg times D1. Do you agree? So that way you can solve depending of what is given to you. If it's not enough to solve, then you can use the force equilibrium that say everything up will be equals everything down. And again, it's in magnitude. So what is up? You have N1 and then N2, and you have the weight. So that's called static equilibrium. Now the fulcrum can be placed wherever you want. You can place it here. It depends what's the question. Right? Push up. Any question? So again, you are using magnitude here, magnitude there. The torque applied by N1 about the fulcrum is 0 because it doesn't rotate anything. And it's a normal force. You squeeze the ground, it's going to squeeze back. Okay, what else? Momentum is a vector. It's going to be mass times velocity. So Newton called it the quantity of motion. Okay, and so you have, remember, you have the kick. So the impulse. So impulse is force times the time equals the change in momentum, which is mass times the final velocity minus initial velocity. And the thing I can try to trick you, and I always trick students with that. Remember, when you have a bouncing ball, if it's bouncing, there is more kick. That was the idea of the now I forgot. The paddle, you know, the water mill that was going faster because the water was bouncing Pelton, the Pelton wheel. So anyway, when it's bouncing off, you always have more change in momentum. You're gonna have more kick. Okay, so you don't subtract the velocity, you add the velocity because minus times a minus is a plus. Because the enemy of my enemy is my friend. The enemy of my enemy is my friend. So minus and minus is plus. Okay, remember that? So if you are going at 3 meters per second here, and you are bouncing back at 3 meters per second, and the mass is 1 kilogram, okay, so the change in momentum will be 1 kilogram, thank you, the final velocity, which is 3, minus 3, which is 6, because my enemy of my enemy is my friend. Okay, I was teaching algebra back then, so that's what I was saying. Okay. Okay, and then there is this problem that I don't know why people have issues with. I don't find it very hard, but some people find it very hard because of the trick. The issue is never the physics. The issue is the math. Okay, so it's the math. It's not so much the physics. Physics is conceptual. Once you have the concept, it's fine. It's the math. So let's say you are hanging on the ceiling. Okay, you have a mass hanging on the ceiling. Maybe it's the frame. This is your grandma in the frame here. So you have two strings, and here you have the mass mg. So this is a force equilibrium. And you have a tension here, and you have a tension there. So the magnitude is the same, but it's not the same tension because the direction is not the same, but the magnitude T is the same. Okay, because this angle here and that angle there are the same. Okay? So it's a force equilibrium, which means that everything to the right equals everything to the left, everything up equals everything down. So the tension has two components. Okay, so we have an x component here and it has a y component here, and this one has a x component and a y component. So you have the x component will be equals to each other, right? So it's going to be t. So in that case, the x component is going to be the sine. Okay, so it will be sine alpha equals t2 sine alpha, and nothing here, just tell you that t1 equals t2 equals t, because the angle is the same. What is more interesting is up equals down. Okay, so up equals down, so everything up equals everything down. So that will be t1y plus t2y equals mg. So that will be t, it's a cosine. Here we have another cosine equals mg. So you have 2t cosine equals mg. Okay, so then you can use this equation. Okay. If you are confused because I told you the sine is the y and the x is the cosine, that is true only if you take this angle here with the positive x-axis, and you can do that. If you take the angle with the positive x-axis, so yes, the x component is always a cosine, the y component is always a sine. Yes.
In the case that there isn't a tension pulling down, that force would be just the weight.
If you mean if there is no, you want mean like this?
Yeah.
Yes. So if you're hanging this way, yes, the T equals mg. And if the angle is not the same, then you have to use two equations with two unknown, which is a little bit more challenging. And really, if you are totally lost and you don't get it, you just memorize. You just memorize. If you really, really, really don't get it. But you should get it because math is important even for whatever your major is, especially if you are taking the MCAT. We good? And it was test number 2 as well. And there was an assignment, and we did that in class. Okay, finally, kinetic energy equals 0.5 the mass times the speed squared. Kinetic energy is in joules, the mass is in kilogram, and the speed is meter per second. So kinetic energy is proportional to the mass, which means if you multiply by 5 the mass, kinetic energy is multiplied by 5. However, kinetic energy for the same mass is proportional to the speed squared, which means if the speed is multiplied by 5, so if the speed is multiplied by 5, kinetic energy is multiplied by 25. Which means that if you have 3,000 or 3 million joules of kinetic energy for the same mass, so mass stays the same, and if the speed is multiplied by 2, kinetic energy will be multiplied by 4. So kinetic will be, this is multiplied by 4, so that will be 12 million joules. So that's why kinetic energy kills. It's a killer, right? On the I-95, that's a killer. Here, have to be careful. Don't speed up because kinetic energy goes with the speed square. So it will take 4 times more distance to stop. And if you don't stop on time, 4 times more damage. Hospitals, hospital fees, or insurance. Are we good? Okay. What is? Okay, centripetal force again. Let's say something is going around a circle, a mass, maybe it's an airplane going a circle like this. I don't know, you are holding here the string. It's going around a circle like this. So it has a linear velocity here, tangential. Tangential means tangent, so tangent to the trajectory. That means you need a force toward the center. That force is called a centripetal force. It's not a force, it's something has to provide this force. Okay, because otherwise, off tangent, it wants to go. It wants to keep going longer. It wants to keep going at the same speed along the straight line. No, you can't. Okay, you need something here to pull it toward the center. I want to keep going along a straight line. And no, you can't. You need a force to pull this toward the center. So that force in that case will be the tension. It doesn't have to be the tension, but in this case, it will be the tension, and that will be the centripetal force, which is mv squared over r. Okay, so that will be the centripetal force. The centripetal acceleration, so F equals ma. So the centripetal acceleration is v squared over r. So here we suppose that there is no tangential acceleration, which means it's moving. It's a uniform circular motion. Uniform circular motion because it's moving at a constant speed, but you need to pull it toward the center, otherwise off tangent it goes. So we can define a rate of spin, RPM, or revolution per minute, or omega. Omega usually is in rad per second. Okay, angular speed. rotational speed. And you have this relationship V equals R omega. So again, this is in meter per second, this is in meter, and this is rad per second. Okay? So if you are driving a car and you are making a turn, it's the static friction that will provide a centripetal force. If you do not have enough static friction because you go too fast, so you are over the maximum static friction, off tangent you go, and you have an accident. Yeah, you don't want that. So you have to slow drive. So anyway, you can use that equation here. Okay? What else? Yes. Centripetal acceleration, centripetal force. If you are moving at a constant speed, okay, so in magnitude, speed is distance over time. The distance around is 2 pi r. And time in that case will be the period. Period means time for one cycle, and the radius r is this radius r. Yes? Okay. What else? Again, average power is the net work, so energy transfer over the time elapsed, and that could be written as the force applied, so the force providing the power times the average velocity. And do remember that the equation sheet that you want is this one. Oh, and yes, so the work done complete. Okay, the other thing, just remember the work done by a force, okay, it's the force parallel to the displacement times the displacement. However, if the force is making something go slower, the work is negative, okay? So work is negative when it's going to try to slow down a system. Work is positive when the force is trying to speed up the system. Okay? Okay, good. Okay, so anything you don't see on this page, then you can. This is the thing I put here for the equation sheet that you can bring. If you don't see something there, you can memorize it, right? This one is quite complete. There is some calculus, but don't worry about it. But you see here, this is the impulse, this is the change in momentum, and change in momentum, which is the force times the time elapsed, right? mv squared over r. You have the definition of kinetic friction. So anything you don't see here, you can memorize it. I won't have any spare.
Is that sheet on the Dropbox?
It's yes, it's in one of announcements, like yesterday or the day before. Okay, that's it. If